This lesson is on normal distribution. So a normal curve looks like the one below. You may have heard it called a bell-shaped curve. And this represents a normal distribution, which means that there are an equal amount of results below the mean as there are above the mean. In a normal distribution, the mean would be right here at this value, and it would also be the median and the mode. They are all the same value in a normal distribution. The numbers that you see along the bottom are what's called standard deviations, and that means how far away it is from a value is from the mean. So a value that falls right around here would be 1 standard deviation from the mean. A value that falls over here would be 2 standard deviations from the mean. Here would be 3, and then we can do the same thing in the opposite direction. We have something called the empirical rule. And the empirical rule are these percentages that you see here. So the chance that, or the probability that, a value will fall within 1 standard deviation, right, in either direction, within 1, is 68%. The probability that a value will fall within 2 standard deviations is 95%. And the probability that a value will fall within 3 standard deviations is actually, I'm going to change this, it's actually 99.7%. So that's the probability that a value in a normally distributed curve will fall within 3 standard deviations. All right, so now let's see how this is used in solving problems. The time it takes to be served food at a local restaurant is normally distributed with a mean time of 17 minutes and a standard deviation of 2 minutes. Now let's stop right there. A mean time of 17 minutes means that this right here is 17 minutes. And then a standard deviation of 2 minutes means that the next line over, I would add 2. So this would be 19 minutes. And this would be 21. And this would be 23. I can go the other direction, subtracting the standard deviation as I go. So this would be 15 minutes, and 13 minutes, and 11 minutes. So it says approximately what percent of pizzas are delivered between 13 and 21 minutes? So I have to look for those times on my graph. Here's 13, here's 21, and that is within 2 standard deviations. So my answer would be 95%. Now, if that seems easy, that's because it is, but of course we're going to get just a little bit more complicated because sometimes you're in between standard deviations. Sometimes it's not just 1 standard deviation, it's 1.5, or it's 2 3/4. So what happens when we fall in between? Well, we're going to use something called z-scores. And z-scores correlate to these numbers that you see down on the bottom. Now, these numbers are also standard deviation, right? This is 1 standard deviation under the mean, 2 standard deviations under the mean, 3 standard deviations under the mean. These are also z-scores. So a value that is 1 standard deviation under the mean has a z-score of -1. Now, we're going to use a table to look up z-scores, but when you do that, let's say we look up the z-score of -1, which would be right here. You're going to find a decimal on the table, and that decimal is going to tell you the total of all of the percentages up until that z-score. So if I look up a z-score of -1, it's going to give me the sum of 13.5, 2.35, and 0.15. Okay, these 3 are going to be summed together because when I look up a z-score of -1, I'm looking for everything up to that point. So likewise, if I looked for a z-score of +1, I'd be looking for everything up to that point, which means I would be adding this percentage, and this one, and this one, and this one, and this one together. And when I add all of those percentages together, I would get a z-score for the z-score for 1. Okay, so remember that whatever z-score you're looking up, even if it's all the way over here, 2.5 or something like that, it means that you're adding up all of the percentages up to that point. And as we get closer and closer and closer to this edge, if we were to be able to sum all of the probabilities together, all of the percentages for the entire curve, they add up to 1. So the higher the z-score, the closer we're going to get to 1. The lower the z-score, the closer we're going to get to 0. So let's see how this works. And this is the table that we're going to be using. I know it looks complicated, but it's really not. So for example, if you wanted to look up a z-score of -1, like we were saying, here it is, -1.0, and this would be my z-score. Now what if I had -1.1? Well, I would be in this row, but then look at my columns. My columns are the digit that is in the hundredths place. So if I have a 1 or a 2 or a 3 or a 4 that comes after the -1 point, then that's where I would look. So let's say I wanted to look up -1.3. Well, this is -1.0, -1.1, 1.2, so this is -1.3. I'm sorry, -1.03. So here's -1.0, -1.0, -1.01, -1.02, -1.03. If I wanted to look up -1.3, then I would come up here. And this would be the value for -1.3. So now let's see how we can use the table in a problem. So the lifespan of a marmoset is normally distributed with a mean of 14 years old and a standard distribution of 2. Let's stop right there. Let's fill those values in on our chart. So a mean of 14 and a standard, oh, that's supposed to say standard deviation. So make that change. Standard deviation of 2 years. So that means I'm going to have 16 and 18 and 20. And I should probably write them down low. Let me write them a little bit lower so they're closer to the values that they represent. 16 and 18 and 20. And then I could go back the other way, subtracting 2 each time, 12 and 10 and 8. And it says the oldest marmoset was a little over 19 years old, which would fall in this area. And this 2.35, by the way, it's just pointing to this whole area is 2.35, not just right that spot. The oldest marmoset was a little over 19 years old. Approximately what percent of marmosets live longer than 19 years? So I want to know the probability that the marmoset will live beyond this point. So let's put in where 19 would be approximately on our curve. So 19 would be approximately here on our curve. And this is the percent, that blue part right there. Actually, let me do that instead. This little blue piece, this is the percent that we're looking for. So we can find a z-score to find everything that's up to that point, and then we just have to find how much is left over from 1. So let's find our z-score first. To get our z-score, we have to do the value that we're using, which for us is 19. This is going to be our x, minus the mean. So this is our mean. And then we're going to divide by the standard deviation, which is this value here. So we're going to have our z-score will be 19 minus the mean over the standard deviation, which will give us 5/2 or 2.5. So our z-score is 2.5. So now I'm going to go to the z-score table. I'm going to find 2.5, which is right here. And there's nothing that comes after the 5. So this is the value I'm going to use. It's 0.9938. So the z-score, oops, let me fix that. So this z-score correlates to a probability of 0.99, and was it 38? Let me just double check, yes. 0.9938, which means the probability of everything up to this point added together is 0.9938. Now, for the question, we want to know this area over here. So how far away are we from 1? If everything up to this point is 0.9938, how far away are we from 1? Well, I can find the answer to that question by subtracting. So that's what I'm going to do. Because I want to know longer than 19 years, I'm going to do 1 minus my probability, because I want just that tail end at the very top. I'm going to do it on my calculator. 1 minus 0.9938 is 0.0062. If I convert that to a percent, it would be 0.62%. That is the percent chance that a marmoset will live longer than 19 years. Okay, so just to recap, we used our values to find our z-score. We looked the z-score up on the table. We got this value, and that percent, or that probability, is all of this added together. But in the problem, we wanted to know the other side of that. We wanted to know this area right here. So we had to do 1, which is the total, minus what we have up to this point to get the probability that a marmoset lives longer than 19 years. Okay, let's try another one. The height of redwood trees are normally distributed with a mean of 50 and a standard deviation of 8 feet. So here's our mean, and here's our standard deviation. And I'm going to fill that in on my graph. My mean is 50, and then I'm going to go up to 58. And then I'm going to go down 8 to 42. And for this question, it's asking me approximately what percent of trees are between 40 and 60 feet in height. So according to my just approximation down here, 40 would be somewhere around here, and 60 would be somewhere around here. But in order to find those values exactly, we're going to find a z-score for each one. So this z-score should be about -1 point something, and this z-score should be +1 point something. But let's figure out what the exact z-score is. So it's going to be, let's do the z-score for 40 first. The z-score is going to be the value that we're looking at, which is 40, minus the mean, which is 50, divided by the standard deviation, which is 8. So we get -10 over 8, which is the same thing as -5 over 4, or -1.25. Now let's find the z-score for 60. So we would have 60 minus 50 over 8, which is 10 over 8, 5 over 4, or +1.25. So now we're going to look both of those values up on our table. Let's look up the -1.25 first. So negative 1.2 is right here. And this is negative 1.20, 1, 2, 3, 4, 5. Right? And you can see the 5 up here too. So that would be negative 1.25. It's 0.1056. 0.1056. 0.1056. All right, let's find the z-score for positive 1.25. So here's 1.2 and 1.20, 1, 2, 3, 4, 5 is 0.8944. 0.8944. Now remember what we're finding. That means that all of the probabilities added together up to this point would be about 10.56%. All of the probabilities added up to this point are about 89.44%. But we don't want to know those values. We want to know what's between them. So if I want to know just from this point to this point, I could take this probability, the probability that I got for this whole thing here up to this red line, and subtract this part. So I'm going to do my z-score for 60 minus my z-score for 40 so that I can get the part that's in between. So we're going to subtract these. We're going to do 0.8944 minus 0.1056. We get 0.7888, which would be 78.88%. And that is the percent of trees that would be between 40 feet and 60 feet in height. All right. A certain academic scholarship requires an SAT score on the math portion that's in the top 1% in order to be accepted. If the SAT has a mean of 500 and a standard deviation of 115, what's the minimum qualifying score to meet the scholarship requirements? So in this one, we are in essence given the z-score. So top 1%, if we look at that curve again, and actually this shouldn't be quite so much on this side. Let me draw that again. If we look at this curve again, the top 1% would be somewhere all the way over here. This is the top 1%. So everything up to that point is 99%. So we're going to look on our z-score table for a score of 99%, or 0.99, as close as we can get to 0.99. So let's take a look. I'm definitely looking in the bottom of this table because these are where my 0.99 values are. And it looks like the closest I can get to 0.99 is this value right here. And this correlates to 2.3 and 0.03. So 2.33. All right, so that's my z-score. So that's what I'm going to fill in here. So I know that I have a z-score of 2.33. That's going to be equal to the value that I need to get on the test, which I don't know what that is, minus my mean over the standard deviation. And then we solve. So to solve this equation, I'd have to start by multiplying both sides by 115. So 2.33 times 115 is, so I would get 267.95 is equal to x minus 500. And then I continue solving. To solve this equation further, I would have to add 500 to both sides. So I get 767.95 is equal to X. So that is the score that I would have to get on the math portion of the SAT in order to qualify for this scholarship. And that's pretty close to perfect for the math portion on the SAT.